Hello friends, welcome to lecture number 5 of convective heat transfer. In the last class, we were looking at the order of magnitude analysis for the laminar boundary layer. We found that even without solving the entire equation for convection for our laminar boundary layer, we were able to just take the orders of magnitude of the various terms and from that show several results, both of fluid mechanics and of heat transfer. So let's quickly go to the whiteboard and review those. So we found that for the fluid mechanics result, we found that the delta by L is of the order of Reynolds number to the power of minus half. Okay, so the delta by L goes as RE to the power of minus half. So this is one result, from which we also found that the skin friction coefficient, which is the non-dimensional value of the shear stress, goes as RE to the power of half. Okay, so this is one result that we found in the last class. Then the next thing that we did was to look at Prandtl number at different cases. So we found that for Prandtl number much greater than 1, okay, when delta or the momentum boundary layer thickness is much larger than the thermal boundary layer thickness, we found that the Nusselt number goes as RE to the power of half Prandtl to the power of 1 by 3. And in another case, when delta T is much larger than delta, which is the case when Prandtl number is much less than 1, we found that Nusselt number goes as REPR raised to the power of half. Okay, and we also said for the two going of the same order, we would again have the U of the order of U infinity, and therefore the same result would come. So for Prandtl number greater than and of the order of 1, you will have this result, and Prandtl number much less than 1, we have the result of, Prandtl number less than of the order of 1. Prandtl number less than and of the order of 1, we have this result, and for Prandtl number much greater than 1, we would have Nusselt number is of the order of RE to the power of half Prandtl to the power of 1 by 3. Okay, so these are the results that we looked at in the last class. Now in this class, we will be looking at a more rigorous solution of these equations and look at a different method of classical boundary layer equation solution. So let's start with the boundary layer equations. The boundary layer equations, what do they look like? They look like U del U by del X plus V del U by del Y is equal to nu times del squared U by del Y square is a momentum equation. Of course, the continuity equation is del U by del X plus del V by del Y equal to 0. So this is the continuity equation. And this is the momentum equation. In x direction. Momentum equation y direction, of course, we said is negligible. And in the energy equation, we write U del T by del X plus V del T by del Y is equal to alpha del squared T by del Y square. So these are the three equations that we'll be looking at, 1, 2, and 3. What we will be taking advantage of in today's method is what we call as the similarity. So the method that we use today would be called the similarity solution. So what is the similarity that we are going to look at in today's case? So suppose this is a flat plate. Okay, it's not looking as flat as it should. So let's draw that again. Okay, that's probably better. So if I have only the momentum equation, let's first look at. So there is a boundary layer that we actually talked about. If I look at velocity profiles at different locations, let's say here and here, okay, drawing straight lines is becoming an issue. So the velocity profile here looks like something like this. So here the velocity is u infinity constant, and here it decreases like this, and here the velocity profile looks something like again like this and coming to this. So if I scale the velocity boundary layer thickness with respect to, if this is delta at x1, and so this is x1, so this is the x direction, and this is, let's say, x2. This is the thickness is delta at x2. So if I plot, if this is the y direction, so if I write this is u infinity, I write as a plot u by u infinity, which is the non-dimensional velocity in this, so it goes from 0 here to 1 here, against y divided by the delta of that x. Then what we will get is the same profile just expanded to go here. So here we have this thickness, and here we have this thickness, but the velocity goes from the same 0 to same 1 at a larger this one. So if I normalize with respect to that, I find that the velocity profiles completely collapse. So if I draw the boundary layer profile, this is, let us say, y by delta, and this is u by u infinity. Okay, so this is 1.0 for this, and this is, let us say, 1.0 for this. Then I would get a velocity profile which is exactly like this for all the locations, whether it is here, whether it is here, whether it is here, whether it is here. At all locations inside the boundary layer, they will all collapse to the same velocity profile, which is u by u infinity versus y by delta. So this basically means that these boundary layer profiles are self-similar, okay, and are only scaling themselves with respect to the delta. So if I want to get the boundary layer solution, that is the solution for this equation, which is a function of both x and y, instead of getting it as a function of both x and y, I can just get it as a function of y by delta of x. So this delta is a function of x. So this delta only, x only acts as a scaling function. Okay. So the delta, which actually goes as rex to the power of minus half, is what we saw in, delta by L goes as rex to the power of minus half. That's basically what we saw in this page. Okay, so the delta x, delta by L goes as re to the power minus half here. So at any x, so delta x by x goes to the power of rex to the power of minus half, where the re is written in terms of, here it is u infinity L by nu. If I write it as REL, with respect to x, if I write, it will be REX is equal to u infinity into x by nu. Okay, so in the present case, if I look at the location at any particular, the boundary layer at any x, you write the delta of x. This delta of x would be, delta by x would be REX to the power of half. Okay, so at all the x, so it will just scale with x. So basically, if I am able to write, if I'm able to create a non-dimensional variable called eta, which is y by delta of x, basically that. So if I write delta is actually x times rex to the power of minus half, then I'll be able to define this similarity variable. So let me do that. The similarity variable y by delta. So eta is y divided by delta of x, okay, which is equal to y divided by x into rex to the power of minus half, okay, which is nothing but y divided by x into rex to the power of minus half will be rex on the top, so it will be u infinity into x by nu under root. Okay, so this, then what happens, there is an x in both sides which will get cancelled, so you would get actually y divided by square root of x nu divided by u infinity. Okay, so this is basically what you would get. So this eta would actually be y by square root of x multiplied by this. Okay, so this is the expression that you would basically get. So delta would be, or you can write the same thing with u infinity at the top also. So this will be y multiplied by square root of u infinity by nu x. Okay, so this is the expression for the non-dimensional variable eta. So if I derive that, then in order to unify the velocities x and y into one, we use what is called the stream function psi. Okay, so what is the stream function psi? Stream function psi is defined in such a way that del psi by del y is u and minus del psi by del x is v. So this will, by defining this stream function, we ensure that the continuity equation is automatically satisfied. How? Del u by del x plus del v by del y is what? It will actually become del u by del x will be del squared psi by del x del y, and del v by del x would be, sorry, del by del x rather. Okay, it's the same anyway mathematically. Minus del squared psi by del x del y, which identically becomes equal to 0. So the continuity equation, that is this is equal to 0, is automatically satisfied by just defining the stream function psi. Okay, so now what is psi then? Psi is in some sense u dy, okay, integration. So this psi is going to be of the order of u infinity into delta, right? That is the order of magnitude, because the dy is the boundary layer, so of the order of delta. So if I define this delta, this delta goes as x into rex to the power of minus half. So this will be u infinity into x into rex to the power of minus half will be square root of nu by u infinity x. Okay, so then what happens? This u infinity x, they get cancelled inside the square root. So this becomes of the order of u infinity x into nu. So I can non-dimensionalize psi with respect to this to get a function f, which is psi divided by square root of u infinity x into nu. Okay, so now if I use these two variables, that is f and eta, I'll be able to unify both u and v into the function f, because through psi I'll be able to do that using this definition of psi, that is the stream function. Psi is called the stream function. Okay, so f is nothing but a non-dimensional stream function which is normalized with respect to square root of u infinity x and nu. Okay, so this is again a function of x. So you doing this, you can actually reduce the governing equation which we started with, that is this governing equation for u into as a simple ordinary differential equation whose solution will give me the plot that I am looking for, which is basically this u by u infinity as a function of eta, because y by delta is eta now. Okay, and now u by u infinity will be representing or expressing in terms of f. Okay, so that's basically what we will be doing. So what does the mathematical treatment then become? So let me, now that I have defined the value of eta, I can say, okay, so let me take the next fresh page and do it. So eta is equal to y multiplied by square root of u infinity by nu x. So if I write del eta by del y, this will be equal to square root of u infinity by nu x. Okay, and similarly del eta by del x will be y into square root of u infinity by nu, which is constant with respect to partial derivative, and 1 by root x will become x to the power of minus half, so it will become minus half x raised to the power of minus 3 by 2. Okay, so if I simplify this, then I will be getting this x to the power of 3 by 2 will become x to the power of half into x and in the denominator. So the x to the power of half will go inside this, so it will become y into square root of u infinity by nu x, which will be nothing but eta itself, and in addition to that there will be a minus 1 by 2x. Okay, so this will actually become minus eta divided by 2x. Is that correct? So that is the expression for this. So now let's do all the other similar partial derivatives and then we can put things together. Now u is nothing but del psi by del y, which is equal to psi is equal to square root of u infinity nu x into f. Okay, because we had said f is equal to psi divided by square root of u infinity nu x. That's what we said. F is equal to psi divided by square root of u infinity nu x. So this will go this side. So psi will be equal to this. So if I do this, then if I write del psi by del y, okay, so what will I get? I'll get this is solely a function of x, and therefore this will stay as it is, square root of u infinity nu x, and this f is a function of eta, so I can write it as df by d eta, because ef is a function only of eta, and then I'll write del eta by del y. Okay, and for del eta by del y I substitute from here, so that will be equal to square root of u infinity nu x multiplied by square root of u infinity divided by nu x, right, multiplied by df by deta. So what will happen? This nu x will get cancelled between these two, and this will become just u infinity. This will be u infinity into f prime. Okay, so df by deta I write it as f prime, so it will be u infinity to f prime. So basically what I get is u is the same as u infinity to f prime, or rather f prime is equal to u by u infinity. Okay, which is basically one of the things that we actually set out to do in this plot. We basically have to get this is f prime. Okay, so f prime as a function of eta is the plot that we are actually looking at. So f prime versus eta is this plot. So finally what we need to get as a velocity profile is this as a function of eta. Okay, that is u. Similarly, let's get V. V is minus del psi by del x is equal to, now if I have to derivative, okay, there are two functions of x here. This is also a function of x, this is also a function of x. So there will be a product rule that will apply. So it will be a minus sign. Let me take it inside the bracket. So it will be f multiplied by square root of u infinity nu, and this is half x to the power of minus half. Okay, so that is the first one, plus the second one is square root of u infinity into nu x into, this will become df by d eta into del eta by del x. Okay, and what is del eta by del x? Del eta by del x is nothing but minus eta by 2x, as we have obtained here. Okay, this one, and so we'll use that here. So this will become the minus sign, I can take it in. So I'll get a minus f by 2, okay, and this will become square root of u infinity nu by x. So that is the first term. I'll take the minus sign again here, and there is another minus that is coming from here, so it will become again plus. Okay, square root of u infinity nu x multiplied by eta by 2x into f prime. Is that right? So that's the term that I'll get. This is V. Now what will happen? This 2x, the x will cancel part of this, half can be taken out. So this will be half of, and there will be one x below that will be there. So you will again get u infinity nu divided by x square root. So I'll just write that u infinity into nu by x in the square root multiplied by minus f plus eta f prime. Is that correct? So this is your V. V is equal to half square root of u infinity nu by x multiplied by minus f plus eta f prime. So this is your V. So u is simply u infinity to f prime, and V is this complex function. Now let's get the other terms, because for writing this equation you need not just u and v, but also get del u by del x, del u by del y, and del square u by del y square. So let's get all those three. Okay, so now let's take a fresh page. Del u by del x is del by del x of, let's write, this is u infinity to f prime. Okay, so from this page we wrote that u is u infinity times f prime, so we'll just take that here. Okay, this is del by del x of that. So u infinity is a constant, so we can take that out. U infinity into, it will become f prime is df by d eta, so it will become f double prime d square f by d eta square into del eta by del x. And from here, what is del eta by del x? Del eta by del x is minus eta by 2x. So we'll just write that here, which is equal to minus u infinity into f double prime into eta by 2x. Okay, so that is del u by del x, which becomes u infinity by 2x with a negative sign into f double prime to eta. So what is del u by del y? Del u by del y is del by del y of u, which is del by del y of u infinity f prime, okay, which will be equal to, again, u infinity is a constant, so you can just retain that here, and f double prime will come, of course, and multiplied by del f by del eta by del y, and that is equal to, and what is del eta by del y from here? Del eta by del y is square root of u infinity by nu x. So we'll just write that here. So u infinity into square root of u infinity by nu x multiplied by f double prime. Okay, that is del u by del y. Now if I want to write del square u by del y square, which will be del by del y of del u by del y. Del u by del y is this, which is u infinity square root of u infinity by nu x multiplied by f double prime. And since none of this is a function of y, I can just take them out. So u infinity into square root of u infinity by nu x multiplied by f triple prime you get, and multiplied by square root of u infinity by nu x, which is del eta by del y. Okay, so it's basically this is d square f by d eta square, so it becomes d cube f by d eta cube into del eta by del y, and del eta by del y is square root of u infinity by nu x. So if I combine these, this actually becomes u infinity by nu x, so that will become a u infinity square divided by nu x into f triple prime. So now if I substitute all of this into the original governing equation, so the original governing equation is u del u by del x plus v del u by del y is equal to nu del square u by del y square. So I'll get u del u by del x where u is u infinity f prime into del u by del x is here, which will be minus u infinity divided by 2x into f double prime theta. This is u del u by del x plus v del u by del y. V is here. Okay, this is half square root of u infinity nu by x multiplied by minus f plus eta f prime. Okay, so let's copy that here. Square root of u infinity by nu x into half multiplied by minus f plus eta f prime minus f plus eta f prime. This is v, and multiplied by del u by del y, which is u infinity into square root of u infinity by nu x into f double prime. Okay, so this is u del u by del y. This is a plus, right? Because there's a plus here, v into del u by del y. Okay, this is equal to nu times del square u by del y square. So this del square u by del y square is this u infinity square divided by nu x into f triple prime. So this nu gets cancelled with this nu, so you get a u infinity square by x. So now let's simplify all of this. So in this one I have a u infinity, so u infinity square. In this one I have a u infinity, a root of u infinity, root of u infinity. So this u infinity square gets cancelled throughout. This with this, and in the denominator there is a x here. Here there is a root x and a root x. So this x, x and x will get cancelled. Okay, so that is done. So the right hand side has only f triple prime, and the left hand side you have f double prime eta. Okay, this is a plus quantity, and here a half. So half f double prime eta, and here you have a half and sorry, this is a minus here. So you have minus half f double prime eta, and here you have a plus half f double prime eta. So this term gets cancelled with this term entirely. So what remains therefore is f triple prime here, and there is a half f double prime with a minus sign. Okay, so if I take both to one side, I'll get f triple prime plus half f double prime equal to 0. That is the equation that I get. So this is the similarity equation that I get from the original equation. Okay, so this is a similarity equation, solving which you can get the profile of f and therefore the velocity profile f prime versus eta. Now, what are the boundary conditions for this equation? So the boundary conditions you had was u is equal to v is equal to 0 at y equal to 0, and u tends to u infinity and v tends to 0 at y tends to infinity. This is the condition that you would have. So if I translate this into the conditions for f, the stream function actually is integral of u dy. So if u starts from 0 at the wall, so I can say f also starts from 0 at the wall, f is equal to 0, and f prime of course is velocity u, which is 0 at eta equal to 0, because eta equal to 0 is the same as y is equal to 0, and so at y is equal to 0 the velocity is 0, so f prime u is 0, which is f prime, because u is u infinity into f prime. Okay, so when u is 0, f prime is also 0. So that is that. And since f is integral of u dy from, let's say, 0 to y at any location, so this integral we can start with the f value arbitrarily as 0 at y is equal to 0. Okay, so that's why the condition of y is equal to 0, f is equal to 0 also comes. So this is one condition. The other condition, of course, is that your u goes to u infinity, or u by u infinity goes to 1. So f prime goes to 1. F prime goes to 1 as eta tends to infinity. Okay, so these are the three conditions. So you have a third order equation, you need three conditions. So you use these three conditions and solve. Unfortunately, this is not available at the y is equal to 0 condition. So you'll need to guess a value of f double prime at 0, which is an unknown. Okay, and iterate until such time that f prime at infinity becomes 1. So that's how you do that. So you analytically cannot solve this equation. You normally use a numerical method to solve this equation. So it's solved using what is called matched asymptotics. Okay, where in the outer region u is all equal to u infinity, and in the inner region u starts from 0 and goes to u infinity. So you match u is equal to u infinity and find the edge of the boundary layer, which is the y is equal to delta. Okay, so that's how you do it. Numerically, you use a shooting method plus any ODE solver, such as, let's say, RK4 method, Gekota for a fourth order, or any other method which will be used for going from eta is equal to 0 to eta tends to infinity. Typically the eta tends to infinity will be in the range of something like 5 or 6, eta is equal to 5 or 6. So you just do that and obtain. So when you do that, you actually get f double prime at 0 to be equal to 0.332. Okay, so this is what you will get as part of the fluid mechanics solution. Okay, so once you do that, then you will be able to plot my straight lines are all going haywire. So if I plot eta here and f prime here, okay, then this is, let's say, f prime is equal to 1 and this is, let's say, eta equal to 1. So then the boundary layer profiles should actually go and meet here. Okay, so this is your profile that you'll get. This is basically the same as this way, except that the XY axis I have swapped. So you are getting the profile like this. So this is how the F prime versus eta plot comes, and the gradient here, F double prime at 0, gives me this. Okay. Now, from the fluid mechanics solution, if I want to get the shear stress at the wall, tau wall is mu del u by del y at y is equal to 0. And if I want to write this in terms of the non-dimensional values, the del u by del y, we have said, is this one. Del u by del y is this one, which is u infinity to square root of u infinity by nu x into f double prime. Okay, so at y is equal to 0, so we'll write that from here, mu times, so if I want to normalize, non-dimensionalize this, you write actually 1 by half rho u infinity square, which is the non-dimensional form of this. I call this as the skin friction coefficient, CF. Since we are doing everything in non-dimensional terms, this will be equal to tau wall by half rho u infinity square. So this will be mu divided by, let's say, half rho u infinity squared multiplied by u infinity into square root of u infinity divided by nu x into f double prime at 0. Is that correct? So that's basically what you get from this expression. U infinity multiplied by u infinity by nu x into f double prime, and we are looking at y is equal to 0, so this is f double prime at 0. So if I put that here and write f double prime at 0 is 0.332, so what will I get? There is a u infinity square and there is a u infinity and root of u infinity. So if I cancel these, I'll get a root of u infinity in the denominator, right? And mu by rho is nu, which is in the numerator. There is a square root of nu in the denominator, so there will be a square root of nu in the numerator, and this x will stay in the denominator. This half will become 2, so the 2 into 0.332 becomes 0.664, so this becomes equal to 0.664 multiplied by square root of nu by u infinity x. Okay, so this is CF at any x. Okay, so this is at any location x. The CF at any x is this. This is nothing but this is 1 over RE to the power of half. So this is 0.664 RE to the power of minus half. Okay, so this, if you remember correctly, in page number 34, let's go back there. By order of magnitude analysis, we had obtained that CF will be of the order of tau wall by rho infinity square CF will be of the order of RE to the power of minus half, and that's exactly what we have found in page number 43 now, that you get CF is going to be of the order of RE to the power of minus half. So that multiplied by 0.664 is a constant that we have got by solving it numerically. Okay, so that is the fluid mechanics result for this problem. Now, if I look at the energy equation next, because I need to get the boundary layer solution for the energy equation. So then I'll have to start with u del t by del x plus v del t by del y is equal to alpha del squared t by del y square. So here I know u and v in terms of f, so I'll be able to write from this thing, u is u infinity to f prime and v is half square root of u infinity nu by x multiplied by this. So they will be as they are. And if I non-dimensionalize temperature, theta is equal to T minus T infinity divided by T wall minus T infinity. Then T becomes equal to T infinity plus T wall minus T infinity multiplied by theta. So my del T by del X would be equal to, so if T infinity is a constant, and if I don't consider T wall to be a constant as our general case, then T wall minus T infinity will be a function of X. So when I write this, the T infinity will give nothing, but this will have a product rule. So I'll have a del theta by del X into T wall minus T infinity, okay, plus theta multiplied by del X of T wall minus T infinity. These are the two terms that I'll get. Now if I want to write it in terms of eta, I'll get a theta prime, which is del d theta by d eta into T wall minus T infinity multiplied by del eta by del X. And what is del eta by del X? Del eta by del X is minus eta divided by 2x. So into minus eta by 2x, that is the first term, plus theta into, I'll just keep it there this way because it's only a function of x. It's del by del X or d by dx of T wall minus T infinity. Because T wall minus T infinity is only a function of x and not a function of y. So I'll write a total derivative and keep it there. Okay, so this is dt by dx. What is del t by del y? This will be equal to, if I differentiate with respect to y, T infinity is again a constant and T wall minus T infinity is independent of y. So it will just be T wall minus T infinity into del theta by del y, which will be theta prime multiplied by del eta by del y, and del eta by del y is square root of u infinity by nu x. Square root of u infinity divided by nu x. Okay, so this is del t by del y. Now del square t by del y square would be equal to, this is again a constant, so I can just write it like this, T wall minus T infinity and multiplied by square root of u infinity by nu x is again a constant, so it will become theta double prime multiplied by del eta by del x again, del eta by del y, which is square root of u infinity by nu x, which will actually become u infinity by nu x multiplied by T wall minus T infinity into theta double prime. Okay, now I can substitute all the values that I have. Let me write down the u and v expressions also here. I know u is equal to u infinity into f prime, and I also know v is equal to half of square root of u infinity by nu x multiplied by minus f plus eta f prime. Is that correct? Yeah, half of square root of u infinity nu by x, sorry, u infinity nu by x into minus f plus eta f prime. Okay, so it's minor correction here, u infinity nu by x. Okay, so I substitute all of this into the first equation that is here. So then what do I get? I'll get it on the next page. U infinity f prime multiplied by del t by del x. Del t by del x is these two terms. So it is with a negative sign here, minus theta prime by 2x into t1 minus t infinity. Minus eta theta prime multiplied by t1 minus t infinity by 2x. Plus del theta by del x, d by dx of t1 minus t infinity into theta. So this is u del t by del x plus v del t by del y will be plus v is this half of u infinity nu by x into this half square root of u infinity nu by x multiplied by minus f plus eta f prime. This is v multiplied by del t by del y is theta prime into t1 minus t infinity into square root of u infinity by x into theta prime into t1 minus t infinity multiplied by square root of u infinity by mu x, and that is equal to the right hand side, which is alpha times del square t by del x squared, which will be u infinity square divided by nu x. So not u infinity square, it's actually u infinity divided by nu x multiplied by t1 minus t infinity into theta double prime. Is that right? So this is u infinity by nu x into t1 minus t infinity to theta double prime. Okay, now let us try to simplify this. So you will actually have a u infinity, there is a u infinity here, and there is a square root of u infinity, square root of u infinity here. Okay, so the u infinity would get cancelled throughout. Okay, and there is a square root of nu and square root of nu would get cancelled between each other here. Okay, and here this alpha by nu will become a 1 by Prandtl number. Let me see. Okay, there is a t1 minus t infinity. If I take it to the left hand side, so I'll get on the right hand side theta double prime divided by Prandtl number. Okay, which is equal to, if I take it to the other side, this t1 minus t infinity, and let me put it into this term. So this t1 minus t infinity will get cancelled against this t1 minus t infinity. So I have a minus f prime eta theta prime divided by 2x. Okay, there is also x here, which I'll have to take it to the other side. So this x also will get cancelled. There's x also here, which is t1 minus t infinity divided by x is what I'm taking to the left hand side. So an x by t1 minus t infinity will come, so that will get cancelled against this. So I'll only have f prime eta theta prime by 2 with a minus sign, so that is this term, plus the f prime theta multiplied by d by dx of, so this will get multiplied by t1 minus t infinity, or the x by dx divided by t1 minus t infinity. x divided by t wall minus t infinity multiplied by d by dx of t wall minus t infinity. Is that right? Yes. Plus, okay, what will happen? There is a minus f plus eta f prime into theta prime multiplied by this t infinity, t minus t infinity and x will get cancelled. There will be a half that is remaining. Okay, x by t wall minus t infinity will get cancelled. We'll get a half remaining. So now, if I look at these terms, there is a minus f prime eta theta prime by 2 and there is a plus f prime eta theta prime by 2. So this term will get cancelled against this one. Okay, and there is a minus f theta prime by 2 that is remaining, and there is another term which is in terms of x and d by dx. So unless this term actually becomes a constant, this equation doesn't look like a similarity equation because x is not getting eliminated. So for similarity solution, to be possible, this thing in the circle has to be a constant, which is x by t wall minus t infinity into d by dx of t wall minus t infinity should be equal to some constant m. Okay, or in other words, this happens if I take dx by x to the opposite side and do the variable separation, then I'll get t wall minus t infinity is equal to c into x to the power of m. Okay, so this is the thing that you will get. Okay, how do you get that? Because you get dx by x is equal to, or m into dx by x is equal to d of t wall minus t infinity divided by t wall minus t infinity. So this basically gives you log of t wall minus t infinity is equal to m log x plus c. Okay, so if I take out the logs, so if I write it as log c, okay, so then I get c x to the power of m on the right hand side and t power of the logs. If I remove, I get this expression. Okay, so under conditions that t wall minus t infinity is equal to cx to the power of m, this will become a similarity solution, but otherwise this will not be a similarity solution. Okay, let's take the simplest possible case where t1 minus t infinity is a constant, where m is equal to 0. So t1 minus t infinity is a constant, or t1 is a constant. Then it is a similarity solution. In which case, this term will automatically become 0 because d by dx of t1 minus t infinity is 0. In which case, the governing equation will basically reduce to this is equal to minus f theta prime by 2. Okay, so let's do that on the next page. For m is equal to 0, t1 minus t infinity is constant, then d by dx of t1 minus t infinity is 0, then theta double prime divided by pr is equal to minus half of f theta prime. Is that correct? Minus half f theta prime is this. Okay, so, or if I bring both to one side, so it will become plus, I can remove that minus half, and I can say this is equal to 0. Or if I multiply throughout by Prandtl number, I'll take out this PR here and write it here. Okay, so to make it look neat, this is so theta double prime plus PR by 2 into F theta prime is equal to 0. And what are the boundary conditions? At eta equal to 0, T is equal to T wall, so T wall minus T infinity T by T wall minus theta is equal to 1, right? And at eta tends to infinity, theta goes to 0. Okay, so if I look at this in comparison with the first equation for fluid mechanics that we got, F triple prime plus half F double prime is equal to 0, with at eta is equal to 0, F prime equal to 1, F prime equal to 0, and at eta equal to 1, F prime equal to 1, I'll find that the two equations will be identical when Prandtl number is equal to 1, provided F prime is 1 minus theta, right? So for Prandtl number equal to 1 and F prime equal to 1 minus theta, or F double prime equal to minus theta double prime, okay, you get the same solution for fluid mechanics and heat transfer. So this is what you call as Reynolds analogy. And the temperature profile, theta profile, would be 1 minus F prime. So if I plot okay, so if I plot eta versus theta, okay, and this is 1, the F prime was looking like this, so the theta would be 1 minus that, so it will be 1 here and it will go to 0 as you go on this one. So this is your eta equal to 1. So this is your theta profile, which will be basically the opposite of F prime profile. Okay, that's basically what we are basically saying, and the gradient of here this one and the gradient of here this one will be just the opposite of each other. Okay, and so this will be F double prime at 0 is 0.332, which will be equal to minus theta prime at 0. Okay, so this is basically what you get from the Reynolds analogy. So Reynolds analogy basically is the analogy between the momentum transfer and heat transfer. And when Prandtl number equal to 1, and what is Prandtl number? Prandtl number is nu by alpha equal to 1. So basically you mean to say that when the momentum diffusivity nu is equal to the thermal diffusivity alpha, then the two equations which are here, let's look at those two equations. Yeah, so these two equations, when nu is equal to alpha, then these two equations become more or less identical, and that u and t would typically have the same solution. U is nothing but F prime into U infinity, and T. So basically the profile just becomes 1 minus this, so it becomes actually, if this is 1, this is 0, and this is 0, so you get a profile which is more like this. So this is your theta profile, and this is your F prime profile. That's the thing that we have drawn there. Okay. So these two equations become same, and therefore the solutions also become similar. So in the non-dimensional form also, these two equations become the same. Okay, in the non-dimensional form also, these two equations becomes the same, provided I write F prime is equal to 1 minus theta. So I just write theta is equal to 1 minus F prime in this expression. Then I'd get theta double prime, and this would get the same answer. So okay, that's the result that you would get. So the same equation, and therefore the same solution, except that there is a 1 minus thing here. That's the thing I get. So let me write down for the heat transfer. For the heat transfer, we would normally write the Nusselt number, or the non-dimensional heat transfer coefficient, NUX. Okay, this NUX is going to be Hx multiplied by x divided by k. This is the expression that we would write, where Hx is defined using the Newton's law of cooling. Hx at any given location x multiplied by T wall minus T infinity is going to be equal to minus k into del T by del y at the same x, at y is equal to 0. Okay, so now if I substitute for del T by del y from the expression that we just derived, del T by del y is T wall minus T infinity theta prime into square root of u infinity by nu x. So this is going to be equal to minus k into T wall minus T infinity into theta prime multiplied by square root of u infinity by ux. So if I look at this and simplify, nux, which is hx into x by k, would be actually equal to, so if I cancel out the T wall minus T infinity between these two and bring the k here and multiply by x, then I would get a theta prime with a negative sign multiplied by x into square root of u infinity by nu x. Okay, so this x will also become, so this will actually become equal to minus theta prime into square root of u infinity x by nu, and this is nothing but the Reynolds number. So this is at 0. Okay, minus theta prime at 0 into Rex to the power of half. Okay, so this is the expression. Now for Prandtl number equal to 1, we have said that this negative of theta prime equal to at 0 is the same as plus positive of f prime. So minus theta prime at 0 is 0.332 in this case. So this is 0.332. So I get NUX is equal to 0.332 REX to the power of half. Okay, so this is your Reynolds analogy. Or if you write Stanton number, which is actually defined as ST at any x is equal to NUX divided by REX into PR, and here since Prandtl number is 1, so you get this divided by RE, so you get this is equal to 0.332 into Rex to the power of 1, so you will get Rex to the power of minus half. Okay, and from the fluid mechanics result, I know that the Rex to the power of minus half, okay, CF is 0.664 into Rex to the power of minus half. Okay, so 0.332 into Rex to the power of minus half is nothing but CF by 2. Okay, so that's basically what I wanted to show you. So in Reynolds analogy, you will get this is equal to CF by 2. Okay, so STX is equal to CF by 2 for Prandtl number equal to 1 is called the Reynolds analogy. Okay, so this is the result that you get for Prandtl number equal to 1. So let's see what happens at the other Prandtl numbers. So for Prandtl number much greater than 1, okay, so what happens in Prandtl number k is much greater than 1? In the boundary layer, this is nothing but nu is much greater than alpha. So alpha is small, so your thermal boundary layer is thin. Okay, and the momentum boundary layer is very thick. So if I look at the thermal boundary layer, delta T is much less than delta. Okay, so this is your delta T, and delta will be somewhere here. So what happens is that in bulk of the thermal boundary layer, the velocity, the eta is extremely small. Okay, so if I look at the eta coordinate, the eta is very small in the thermal boundary layer. So since eta is extremely small, I can write f of eta. I can expand it using a Taylor series in the vicinity of 0. So I'll get f of 0 plus eta into f prime of 0 plus eta double prime, eta square by 2 factorial into f double prime of 0 plus higher order terms. So since this is a small value of eta, I can neglect the higher order terms, so I can just make it approximately equal to this. And since by boundary condition this is 0 and f prime of 0 is also 0 and this is 0.332, I can say f at any eta is going to be equal to 0.332 eta squared by 2. Okay, so I can use this in the solution. And what happens when Prandtl number is much less than 1? When Prandtl number is much less than 1, it's the opposite that happens. That is, the thermal boundary layer is much thicker and the velocity boundary layer is extremely small, so much so that the velocity inside the thermal boundary layer is almost everywhere equal to u infinity. Okay, the velocity boundary layer is so small, after that it's all u infinity. So u by u infinity is equal to 1 in most of thermal boundary layer because delta T is much greater than delta, and inside the delta only you have the u less than u infinity, but after outside delta this is so most of the thermal boundary layer you have a velocity u by u infinity which is 1. So this u by u infinity is nothing but f prime. Okay, so df by d eta is equal to 1, or if I integrate this and write f is equal to eta in most of dpi. Okay, so there is f is equal to eta here and there is f is equal to 0.332 eta square by 2 in this one. Now using this we should be able to get the expression for the Nusselt number by solving the energy equation. Okay, so what does the energy equation look like? The energy equation looks like this one. Okay, theta double prime plus Prandtl number by 2 f theta prime equal to 0. So let's try to solve that equation. Theta double prime plus Prandtl by 2 f theta prime equal to 0. So now let's try to do separation of variables here. So if I write phi is equal to d theta by d eta, which is theta prime, then I can write this is d phi by d eta is equal to minus Prandtl by 2 into f into phi. So if I separate variables, bring the phi here and take the eta here, then I get d phi by phi is equal to minus pr by 2 into f d eta. So now if I try to integrate this from 0 to eta, okay, so then what I'll get this is log phi at eta minus log phi at 0 is equal to, the integral will be, the Prandtl is a constant, so it's minus pr by 2 into integral from 0 to eta of f d eta, let's write a dummy variable here because the limit is eta. So f d eta tilde. Okay, so this is the expression. So if I take exponents of both sides, I'll get phi at eta divided by phi at 0 would be equal to this in logarithms. So I get phi at eta is equal to phi at 0 into e to the power of minus pr by 2 integral from 0 to eta of f d eta prime. Okay, so this is the expression that I get. Now this, let me write it in terms of okay, so this is d phi by d eta, so this is d theta by d eta, sorry, is equal to, this is theta prime at 0, which is an unknown here. Okay, this is the gradient of temperature at 0. This is unknown because the same solution is not the same as a fluid mechanics solution. In the Prandtl number equal to 1 case, we took it from a fluid mechanics solution. Here we cannot do that. So this is equal to this. So this is an unknown value which we have to evaluate. So now let's integrate this again. So that eta would go here. So I'd integrate this between 0 to infinity. So theta at infinity minus sorry, let me integrate between 0 to eta again. Okay, so this is theta at eta minus theta at 0 is equal to, so it will be the integral of this term. So phi of 0 and integral from 0 to eta of exponent minus pr by 2 integral from 0 to, now this is also eta, so let's make this into eta tilde double tilde f d eta tilde d eta double tilde. Okay, so these are basically dummy variables. So eventually you have to get it as a function of this limit that is here. Okay, so now theta at 0, we know from the boundary condition this is equal to 1. So I take this 1 here. So theta at any eta, this is the function that I am trying to solve for, which will be 1 plus theta prime at 0 multiplied by integral from 0 to eta of whatever you have written here. Now I can use the other boundary condition, which is theta as eta tends to infinity is 0. So if I substitute that limit of infinity here, this limit becomes infinity. Okay, so this and theta at infinity is 0. Okay, so I'll be able to write the next expression as 0 is equal to 1 plus theta prime at 0 multiplied by integral from 0 to infinity of exponent of minus pr by 2 into integral from 0 to eta double tilde f d eta tilde d eta double tilde. Okay, so theta double prime of 0 is an unknown, so which can be determined from this integral. So theta double prime or theta prime of 0 is going to be equal to minus 1 divided by this expression integral from 0 to infinity of exponent of whatever. Okay, so if I take this value and substitute into this equation, then I'll get this is minus 1 by the same integral but up to infinity. Okay, so then I'll be able to write theta at any eta is equal to 1 minus integral from 0 to eta of let's write the full expression here, axp of minus pr by 2 integral from 0 to eta double tilde f d eta tilde d eta double tilde divided by the same integral from 0 to infinity exponent minus PR by 2 into integral from 0 to eta double tilde f d eta tilde d eta double tilde. Okay, now in this expression, this integral for f, I use these values from the expression that we just wrote. That is, for Prandtl number much greater than 1, we would use f as 0.332 eta square by 2 in that integral, and for Prandtl number much less than 1, we'll use eta is equal to f is equal to eta in this integral. So for Prandtl number much greater than 1, if I substitute that, this actually becomes 0.332 by 2 into eta squared d eta. So it becomes eta cubed by 3, and 0.332 by 4 will come here, and this eta cubed by 3 will become, so 0.332 by 12 PR into eta cubed d eta, and so it will be e to the power of minus eta cubed d eta, which will get integrated and solved for both the same integrals, only the limits are different. So you would get the expression. So what happens is you basically need only the theta prime at 0 for writing the Nusselt number, because the Nusselt number we wrote just in the previous slide of this. Nusselt number is theta prime at 0 multiplied by Rex to the power of half. So theta prime at 0 is this integral with a 1 by this basically. Okay, so from both of these, just substitute for this f. Prandtl number much greater than 1, f is equal to 0.332 into eta squared by 2, and Prandtl number much less than 1, we substitute f is equal to eta in this integral and simplify. So what you would get is for Prandtl number much greater than 1, you would get a point Nusselt number is equal to Rex to the power of half into theta double prime at 0, and that will give me 0.565, which is actually 1 over root pi, okay, multiplied by Rex PR all to the power of half for Prandtl number much less than 1. Okay, I have written the expression in the opposite place. It is for this one, and for this expression you will get NUX is equal to 0.338 into Rex to the power of half and Prandtl to the power of 1 by 3. And this 0.338 and the expression that you got for Reynolds analogy, which is 0.332, are not enormously different. So what we normally do is to write 0.332 here also, and say that when Prandtl number equal to 1, this also reduces. So this will be Prandtl number greater than and this will be Prandtl number much less than 1, this expression. So this is the expression that you would write for the Nusselt number. Okay. So the next thing that we'll need to write in this is the Nusselt number Hx is something that we know, which is NUX into x by k or k by x. Okay, and this is equal to whatever the NUX expression that you k by x multiplied by some constant multiplied by Rex power of m PR to the power of n. So this is the way you write this. After that, if you want to get the overall average heat transfer coefficient. How do you define that? H bar over the length L is nothing but H bar multiplied by T wall minus T infinity into the length of the plate multiplied by unit width. This will be equal to the integral of Hx into T wall minus T infinity dx from 0 to L. So if I cancel out T wall minus T infinity being a constant, you will get H bar L is 1 over L integral from 0 to L of Hx dx. And since Hx is a function of x, k by x multiplied with this Rex also has u infinity x by nu. So you would get an expression in terms of that. And since this m is half, what you will normally get is this would be equal to twice HL. Okay, so for any x cumulatively, so if you write this is x, okay, this is up to x, then you would get twice Hx. So if for example on this plate at this location I have the heat transfer coefficient as Hx, then the cumulative heat transfer coefficient from 0 to that location, the H bar x will be equal to 2Hx. Okay, so that is the expression that you will get because this Rex has a power, this m is half. Okay, so this will become 2. Okay, so this is basically what you will get. So the expressions that you wrote here, this number will get multiplied by 2 for the overall heat transfer coefficient, because the overall heat transfer coefficient you write as NuL bar is equal to, or NuX bar will be equal to Hx bar into L by x by k, and that would be basically twice that number. Okay, so both the average heat transfer coefficient Nu bar x would be twice NuX. That's what you would get. Okay, so that you will get for both the cases, because in both cases it is actually x to the power of half. And similarly, Cf also would become Cf bar at x would become twice Cf at any x. Okay, so this expression, the Cfx is the local skin friction coefficient and Cfx bar is the average skin friction coefficient from the leading edge up to that point. Similarly, Hx is the local heat transfer coefficient and Hx bar is the average heat transfer coefficient from the leading edge up to that point. Okay, so we'll understand it that fashion. So the expressions that we have got now, actually if you go back to the previous class, the order of magnitude, and verify, the expressions that we have got now have all been obtained in the previous class itself without the actual constants, but the proportionality has been established in the previous class itself. So we said that for Prandtl number much greater than 1, it is Re to the power of half pi r to the power 1 by 3, which we got. And for Prandtl number much less than 1, we said it is going to be of the order of Re pi r to the power of half. And we said that this expression will be valid for both. Actually, you are getting the for Prandtl equal to 1 anyway, it is Re to the power of half, so both of those expressions become typically valid. So that is where we actually arrived at. So this similarity solution method gives you a method by which you can rigorously calculate and obtain the relevant constants of the solutions, and therefore the complete solution. In the order of magnitude analysis, we did not solve any equation, no complexity was involved, but then we were already able to get the form of the solution without those constants. So you can see that you can quickly estimate what would be the kind of dependence using the order of magnitude analysis, but if you want to get the exact constants, then you would need to solve it using the similarity solution method. In the next class, we'll look at an approximate method which is called the integral solution method, where you would assume a simpler profile for the velocity and temperature, and then integrate the profiles in order to obtain the various heat transfer coefficients and skin friction coefficients. Okay, so we'll stop here for this class.